Hello, this is Sachin. Uh, in this video, I'm going to explain the concepts task synchronization and how to choose an RTOS of real-time uh, operating system based embedded system design. Chapter number 10 of Introduction to Embedded System CBKV book. This is a fifth part of this chapter 10. Already 4 are recorded and uploaded to YouTube. Please watch and like and subscribe. So in this video, I'm going to explain the task synchronization and how to choose an RTOS. The task synchronization. The multiple processes may try to access and modify the shared resources in the multitasking environment. So this is all already explained in previous video. So how the task processes or share the resources, shared memory, and some structures we use, a pipe, a message queue, and all. And at the same time, the resources, hardware resources like IO devices, memory, and all these, the other resources, also shared among the processes. And in multitasking environment, it may lead to sometime the conflict or inconsistent results when two processes at the same time try to access the same IO device or try to claim the ownership for present execution of the processes. Then the conflict arises and should not be allowed. The processes should not be allowed to access the shared resources when it is currently being accessed by another process. Otherwise, what happens? The whole process of execution goes into a deadlock. Okay, so that we discuss in the further when we move towards the other concepts in this chapter. So the acting of making the process aware of the access of shared resources by each process to avoid the conflict is known as task synchronization. So how to avoid this deadlock? By synchronizing the task. So how to synchronize the task? There are various techniques. First we'll see what kind of deadlock or what kind of conflict arises. So then we'll try to understand what are the solutions to this kind of deadlock and how the synchronization techniques are implemented to avoid this kind of situations. So first, synchronization issue among the two processes is racing. So here with a simple example, you can see I'm pointing my cursor on that on the slide. So you just observe where there are two processes are created, process A and process B, and one buffer of carry variable is declared, and then this buffer is shared by these two, and at the same time the counter variable is also created of int type, and thus this is updated in this process body, where the process A also uses the same buffer and the counter will update it here, and the process B also use the same buffer and the counter. The racing means the counter, the programmer perspective, the value of the counter will be 10 at the end of the execution of process A and process B, but it need not be always, right? Because when the programmer calls the process A. Imagine that the situation where the process switching takes place from process A to process B happens. The process A also using the same variable as a counting variable, and process B also using the same variable count as a counter variable. Where the process A to process B, when the switching takes place, context switch. Look at here the diagram which is showing when the context switch takes place. At that time the counter is updated, but already the counter is as a global variable, it is declared. It's not local to that process body of the process. Then the process A is executing the counter to counter plus plus statement. The process A accomplishes the counter to count the next higher values. When the context switch takes place, the same counter is updated by the B, and then what happens? The counter is updated for, instead of starting value for B, it has to start from the count from 0 to towards the 10, but it starts from the middle where the A has stopped. It's out update. So this is how the deadlock, that racing condition, then this update A's value and A will update the B value. This is all happens in the racing. Another issue what found in the task synchronization is deadlock. A deadlock is the condition in which a process is waiting for a resource held by another process, which is waiting for resources held by the first process. So deadlock is a condition in which the process is waiting for the resources. Means for example, the process A has hold some resources, IO resources, time being assumed. Then when the context switch takes place, the process B also needs the same. Process A holds the X and the process B holds the Y. Process B needs X and process A needs Y, and the process A and B each other didn't give up their resources, as they hold the X and Y each other. That's why both hold the respective resources, and they complete each other to get the resources held by the respective processes. This situation is called as the scenario of conflict, that what arises in the sharing of the resources is called as a deadlock. That deadlock is similar to that of the traffic at the junction. When the traffic is light is made off, and from all the sides of the lane are allowed to access the lane of the opposite line. So then this is a deadlock when all together from the all side the motor vehicles try to pass that junction, then the deadlock arises. They all are stuck at the same time. And another condition for favoring the deadlock, their mutual exclusion. Mutual exclusion, this is the criteria that only one process can hold the resource at a time. So how the deadlock can be avoided? So favoring the deadlock. Hold and wait. The condition in which the process holds the shared resources by acquiring the lock control and the shared access and waiting for additional resources held by the another process. No resource preemption. So as the operating system cannot take back the resources from the process which is currently holding it, and the resources can only be released voluntarily by the process which is holding the resources. And these are the circular wait. The process is waiting for, just now I explained, the process 1 is waiting for that process 0 is waiting for process 0 is waiting for process 1 resources what it has hold. Process 1 is waiting for process 2, process 2 is waiting for process n, like that, and process n is waiting for the resource held by the process 1. This is called as a circular wait, means all processes are waiting for one more process resource which is held by its next process. So this is called as a circular wait queue. So deadlock is a result of a combined occurrence of the above 4 conditions listed above. And how to handle the deadlock? How to handle the deadlock is, there are various techniques are there to handle the deadlock. The OS may adopt any one of the following techniques to prevent the deadlock condition. So first is ignore the deadlock. So to ignore the deadlock, you have to design what you can say the operating system functions or principles such that there should not be a deadlock, occurrence of a deadlock. So that by that way we can make the deadlock free the system. So this is one way of avoiding or handling the deadlock. So next method is detect and recover. So this approach suggests that the detection of the deadlock situation and recover from it. So for example, how can we do this? There's a traffic jam situation what is explained in the previous slide. So the only situation is to back up the vehicles from one direction and then allow the vehicle from the opposite direction across the junction. So if the traffic is too high, lots of vehicles may have to be backed up to resolve the traffic jam. This technique is known as a backup cars technique. So we have to back up, we have to wait, ask the vehicles to wait for a while till one line is get clear, then one after the other all the lines of the junction has to be clear. So this is one way of avoiding handling the deadlock. Next one is avoid deadlock. Deadlock is avoided by careful resource allocation techniques by the operating system. So operating system has to carefully allocate the resources before allocating the resources to processes. Prevent deadlock condition by negating one for the 4 conditions favoring the deadlock situation. Process must request all its required resources and resources should be allocated before the process begins to execute, not well in advance. So this can prevent the deadlock. Grant resource allocation request from the processes. The processor has to request the operating system to grant the so and so resources. First, operating system has to hold all the resources, and when the process in the ready queue get ready to execute, at that time whatever the resources required it has to allocate. So this is one way of preventing deadlock. So that is called an and to ensure the resource preemption is possible at the system level. This can be achieved by implementing the following set of rules and guidelines. Release all the resources currently held by the processes. If the operating system requests, the processes has to release all the resources IO, memory, if some other resources what it is holding, and that all it has to release. Add the resources which are preempted or released to the resource list. reschedule the processes for execution only when the process gets its old resources. Means when time being assumed process A has holding one resource, now it requesting for the operating scheduler to schedule it to execute the code on the CPU. But before it has to release all the resources, and then the scheduler will schedule the CPU time along with the resources which are required for the process. This is one way of rescheduling the process for execution. And at the same time, apart from the deadlock, another two synchronization issues are there associated with scheduling and process execution. They are task synchronization, related to task synchronization from process to process. They are the Lifelock condition is one among them. The Lifelock condition is similar to the deadlock condition only, except that the process in Lifelock condition changes its status with time. It means the deadlock, once the resources hold, that is not released. That is the problem there. But here, the time to time when the process is executing, it changes its status with time to time, that it may release some resource, it may hold another new resources. So this kind of changes what it will do with the resources holding and releasing, that will create a problem. Lifelock means while executing only it will do all such things. In this Lifelock condition, the process always do something but unable to make any progress in the execution completion. So because of this, the process cannot complete its execution of the code. This is called as a Lifelock. And one more is a starvation. The starvation is the condition in which the process does not get the resources required to continue its execution for a long time. So for time being assumed, process A holds some resource and it is executing repeatedly because it's a higher priority task. So it will resume instantly, immediately after execution of completely. Immediately again it resumes. Then the process B, which is the lower priority task, has to wait for that resource which is required to execute for a very long period of time. That's why it's this is called as this kind of task synchronization issue is called as starvation. So this can be avoided by priority inversion. These kind of issues what I have listed, starvation, deadlock and Lifelock, all these are issues are also avoided by priority inversion. Priority inversion is the byproduct of combination of block based or log based process synchronization and preemption priority scheduling. The priority inversion is the condition in which the higher priority task need to wait lower priority task to release the resources, so which is shared between the higher priority task and lower priority task. And in this condition, the lower priority task has lifted to the same as that of higher priority task priority, and then let the lower priority task to complete its execution, and then the same resource is allocated to a higher priority task, so to let it to finish its execution. The priority based preemptive scheduling technique ensures that the higher priority task is always executed first, but where the log based process synchronization mechanism ensure that the process will not access the shared resources which is currently in use by other process. So this is what is explained, the priority inversion, by this graph. So in this graph you can see where I'm pointing the cursor. You can look at here. So process A is the highest priority, process B is a medium priority, and process C is a low priority. First, the process C come into ready state and it start executing. At the same time, process B and C also come into ready state. B it comes into ready state. It's a mid priority. So and then it start executing process B, and then the process A comes into uh, uh, ready queue. Then it also start, and it is on the all the way to finish it. Before it finishes its execution, at this juncture of time where I'm pointing, it needs the resource. Some resources withheld by the process C. Look at here, and then it is blocked because the resource which is required to finish this execution, task execution, is held by the process C. And then the process C, unless and until it runs its code, it will not release it. So for that, the inversion, the priority inversion algorithm is run, and then the priority of this process C has lifted to process A, so that it will finish. Just look at here, it will finish the it's a program execution or a code execution, and then release the the resources to the its higher priority task, process A, and then the process A finishes, and then it releases that the resources. Then once again the process C start executing. So this is how the priority inversion helps to come out of the algorithm, help to come out of this kind of deadlocks. So task synchronization technique, the process and task synchronization is essential for avoiding the conflict in the resource access and in multitasking environment. That ensures the proper sequence of operation across the processes. And next, and the communication between the process is established for the critical section. The code memory area which holds the program instructions for accessing the shared resources is known as a critical section. So next, synchronization technique used in the real-time embedded system is development. It will take a help of the operating system. That mechanism provided by the operating system is for task synchronization is mutual exclusion. In order to synchronize what is meant by mutual exclusion is in order to synchronize the access to the shared resources, the access to the critical section should be exclusive. That means we have to protect the critical section of the code of the task, any task. The exclusive access to the critical section of the code is provided through mutual exclusion mechanism. So what is a mutual exclusion mechanism is so where the task is run the code that will help to hold that inform the other tasks which are the higher priority, or maybe to intimate that one flag that presently the process 1 is executing. It's a critical part of the code, so till then it won't give the resources, so that the process 2 will request for the priority inversion kind of algorithms to run, and then avoid this kind of situation. And the counting semaphore is if the more number of resources are required for that code to execute, then we have to use the counting semaphore, that if the three resources are required, count 1, count 0, count 1, count 2, count 3, like that. So each resource count associated with the semaphore objects and a decrement by 1 when the process acquires it, and then the count is decremented by when the process is released the those semaphore objects. So the look at here, if it is a counting semaphore, if you are implemented, then the process A uses the resources required are look at here, they have shown here, and for every resource there is one key which uses to hold lock the semaphore, and then and at the end the equal number of keys it has to release, means resources it has to release. If it is locks 3 resources, then it has to release the 3 resources at the end. This slide will give about the idea about how the semaphores are used. Semaphore nothing but a flag intimating the other processes which are executing simultaneously or parallelly or concurrently in the embedded real-time operating system context. So then if the process A, process B, there are 3, process C, there are 3 processes, then process A is executing its critical path part of the code, then it can hold a number of resources as a counting resource. Then next one is a binary resource. So if it is only if it the resource exclusive access to the shared resources by allocating the resources to the single process at the time, and not allowing the other process to access it when it is being used by the process. Now only one process thread can own the binary semaphore at a time, means only one resource can hold the binary semaphore at a time. So that resource fixed resource. So then the binary semaphore, look at here, that diagram will clear. The binary semaphore is with only one binary means single, either 0 or 1. So it holds the resources completely, only one process can use it. So hold the resources completely, and then when it executes all the critical section of the code, and then it release that semaphore. Release means it will make the resources free. Even the higher priority process can preempt and make use of those resources. The only concept here is semaphore concept is to protect the critical part code of the any process. For process A, it may be if it is a lower priority or higher priority process, if it is executing the its critical part of the code, then it holds the semaphore, or means it use the keyword called lock semaphore and release semaphore. The keywords system calls are used in the program, so that part of the code which is very critical in point of view for embedded system, then we have to protect it. For that, this technique is designed for task synchronization. Okay. Then thank you for watching a video. If you liked, please press the like button and subscribe for further update. Thank you.